In this episode, we're going to work through a set of network failures that can look deceptively simple and yet cause the most head-scratching downtime: link problems. These are the situations where you expect basic connectivity, but the interface is down, the link comes up and drops repeatedly, or the machine cannot even reach the first hop reliably. For a brand new learner, these issues feel frustrating because they can happen below the level where applications live, which means your favorite troubleshooting instincts can't get traction until the link itself is stable. The good news is that link problems tend to produce clear patterns once you learn what to look for, especially around negotiation, speed, and duplex expectations, and the difference between local reachability and end-to-end reachability. We'll also build a calm reasoning approach for the common scenario where you cannot ping a server, because that single symptom can come from the cable, the switch port, the route, the firewall, or the server itself. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A strong way to start is to treat the link as a contract between two endpoints that must agree on the fundamentals before any meaningful networking can happen. At the simplest level, the contract is physical and electrical. The cable and port must carry signal, and the interface must detect it. Above that, the contract becomes operational. The two sides must agree on characteristics like speed and duplex, and they must maintain a stable connection without excessive errors. Beginners often jump straight to higher-layer explanations like DNS problems or service outages, but if the link is down or unstable, those layers never get a fair chance. The reason link issues are so important is that they can cause failures that look random, because an unstable link can work for a moment and then fail again, which creates inconsistent symptoms across time. When you adopt the link as contract mindset, you stop treating it as a single on or off state and start treating it as something that can be partially healthy, intermittently healthy, or healthy only under certain conditions. The phrase link down is often used casually, but it actually points to a specific category of failure where the interface does not detect a viable physical connection. This can happen when a cable is unplugged, damaged, or seated poorly, when a switch port is disabled, or when the far end is not actually connected to the same network path you believe it is. It can also happen when a virtual environment presents an interface that exists in software, but is not connected to an active virtual switch or network segment. A beginner can be tricked here because the machine might still have an IP configuration that looks normal, which gives the illusion that the system should work. Configuration does not guarantee capability, though, and link down means capability is missing at the foundation. The best reasoning move is to classify link down as a physical or attachment problem first, which keeps you from wasting time on application diagnostics that cannot succeed until the interface is actually connected in a meaningful way. Even when the link is not fully down, negotiation failures can create a state that is almost worse. The link appears up, but it behaves poorly. Negotiation is the process where both ends decide what speed and duplex settings will be used. And while modern equipment usually negotiates well, mismatches still happen in real environments. If one side believes it is operating at full duplex and the other behaves as if it is half duplex, you can get collisions, retransmissions, and dramatic performance degradation that comes and goes depending on traffic patterns. To a beginner, this can look like the network is slow or unreliable because some simple interactions work and others fail, especially under load. Negotiation issues also show up after changes, such as replacing a switch, moving a cable to a different port, or changing a device configuration that affects how auto-negotiation is handled. The key conceptual point is that the link can be electrically present while logically misaligned, and that misalignment produces errors that ripple upward as timeouts, retries, and apparent randomness. A stable troubleshooting approach for negotiation problems relies on noticing symptoms that correlate with load and direction. When duplex mismatch exists, the network may appear usable for small bursts, then degrade as collisions increase, leading to slow transfers and intermittent failures that feel inconsistent. When speed negotiation is wrong, you may see unexpectedly low throughput or a link that flaps because one side cannot maintain the agreed signaling reliably. Link flapping, where the interface repeatedly goes up and down, is a particularly strong clue that negotiation or physical quality is unstable because it suggests the endpoints cannot sustain a stable agreement. Beginners sometimes interpret flapping as a software issue, but it often points back to cabling quality, port health, or incompatible settings. The best next step logic here is not to keep testing the application, but to confirm link stability as a prerequisite, because higher layer tests are only meaningful when the link is consistently up. Stability first, then performance, then services is a safe order that prevents you from diagnosing ghosts. Now let's connect these link-level concepts to the common field symptom that someone reports first: can't ping the server. Internet Control Message Protocol, ICMP, is a basic network mechanism often used to test reachability, and ping is a way of sending and receiving those messages. For beginners, ping feels like a universal truth test, but it is really just one kind of traffic, and it can be blocked intentionally or fail for reasons that do not match service availability. Still, can't ping is valuable because it forces you to ask where reachability is failing. Is the local link working? Can you reach the local gateway? Can you reach any remote network? And is the target itself responding? The reasoning skill is to treat ping failure as a starting clue, not as a final diagnosis. If the interface link is down, ping failure is expected, and you stop there until link is restored. If the link is up but ping fails to the next hop gateway, you suspect local connectivity or negotiation problems. If ping reaches the gateway but not the server, you move your suspicion outward to routing, filtering, or the server itself. A powerful beginner-friendly method for isolating can't ping is to reason from the nearest dependency outward, because the closest failures are the cheapest to confirm and the most likely to explain everything else. Your machine must first be able to send and receive on the local link, which requires a stable interface and a stable negotiation outcome. It must then be able to talk to devices on the same local network, which depends on address configuration and on the local switching environment. Only after local communication works does routing to remote networks become relevant, and only after routing works do firewall policies and server responsiveness become the primary suspects. This outward reasoning prevents you from blaming remote systems when the failure is local, and it prevents you from blaming the local host when the failure is clearly beyond it. Beginners often invert this order because they focus on the named server, but names and services are late-stage concerns compared to link integrity. When you train yourself to start at the link and move outward, you create a repeatable mental flow that reduces stress and increases speed. Link down and negotiation issues can also create deceptive cases where one direction seems to work better than the other, which is why people sometimes describe the problem as intermittent without a clear pattern. If errors accumulate on transmit more than receive, you might be able to receive some traffic but fail to send reliably, leading to half-working sessions that stall or reset. If the link is marginal, temperature, vibration, or cable movement can change the error rate enough to flip between usable and unusable states. This is why link problems sometimes appear and disappear without any configuration change, which can make beginners suspect software or malware. The safer interpretation is that physical layers can be sensitive and that marginal conditions can present as intermittent failures. A good ops mindset treats intermittent link symptoms as a reason to suspect physical quality, port health, and negotiation stability before chasing exotic explanations. Even in virtual environments, similar principles apply because virtual switches and uplinks can be misconfigured or oversubscribed, producing flapping or degraded behavior that mimics physical instability. The theme is that the link can be unstable for real, understandable reasons. It is also important to distinguish between link-level inability to reach and policy-level refusal to respond, because both can produce no ping response but imply different remediation paths. A server might be reachable and healthy while simply not responding to ICMP due to firewall policy, which means ping is not a reliable measure of service availability in that environment. On the other hand, a complete lack of any response, combined with other symptoms like failure to reach multiple destinations, suggests a more fundamental problem like link instability or routing absence. Beginners often treat ping as a binary oracle, but a better mindset is to treat it as one probe among several layers. The link layer cares about whether frames can be exchanged, while higher layers care about whether specific protocols are allowed. If you assume ping must work, you can misdiagnose a healthy server as down and waste time. If you assume ping never matters, you can miss the clue that the local link is broken. The mature approach is to interpret ping in the context of known policy and observed scope. Negotiation failures also interact with switching infrastructure in ways that can confuse beginners, especially when the local port configuration expects a particular behavior. If a switch port is configured for a fixed speed or duplex and the host tries to negotiate automatically, or if the host is fixed and the switch expects negotiation, the result can be mismatch or instability. This is not about one side being wrong. It is about the two ends failing to agree on the same contract. In some environments, ports are also configured with security features that can disable a port if unexpected behavior is detected, which can look like a physical link problem even though the cable is fine. A careful responder therefore considers that link down might be the consequence of policy on the port, not just a damaged cable. The reasoning move is to remember that modern networks include both physical signaling and administrative controls, and both can result in a link that appears down from the host perspective. When you treat the port as an active participant with rules, you broaden your hypotheses in a productive way without losing focus. The phrase negotiation failures also includes the idea that a link can be up at an unexpected speed, which can create subtle performance problems rather than complete outages. A host might negotiate to a much lower speed due to cable quality, a marginal connector, or a port issue, and the result is that connectivity exists but performance feels broken. In operations, this often surfaces as complaints that something is slow, timeouts occur under load, or transfers stall, even though basic reachability tests seem to work. Beginners can waste time tuning applications in these cases because the bottleneck is below the application. The key conceptual habit is to treat unexpected performance degradation as a potential link negotiation artifact, especially when the timing correlates with a cable move, a port change, or a hardware replacement. This is also where recognizing the difference between throughput and latency matters. Negotiation problems can increase retransmissions and delays, which increases effective latency and can cause timeouts even when the path technically exists. When you connect these symptoms to the link contract, your troubleshooting stays grounded. A reliable first response approach to link problems also includes the discipline of minimizing changes while you isolate, because the link layer is sensitive and changing multiple variables at once can hide the cause. If you swap cables, move ports, and change configuration all at once, you may restore service but lose the ability to explain what fixed it, which makes recurrence likely. In professional operations, the goal is not only to restore service, but to restore it in a way you can trust and understand. That means you make one change, observe the outcome, and use the outcome to confirm or reject your hypothesis. For a learner, this practice builds the skill of controlled experimentation. It also protects you from accidentally creating new issues, such as moving a cable to a port that is on a different network segment or changing a setting that breaks other dependencies. Controlled changes are a form of safety, and link problems reward that discipline because they can be resolved quickly when you identify the right variable. It also helps to connect link reasoning to the earlier concept of scope, because scope is the fastest way to decide whether a link issue is likely. If one host cannot reach anything while nearby hosts on the same switch work fine, suspicion shifts toward the host's link, cable, port, or local configuration. If many hosts connected to the same switch or segment suddenly fail, suspicion shifts toward shared infrastructure such as an upstream link, a switch failure, or a configuration change on the network side. If failures appear only for one destination, link issues become less likely, and routing, filtering, or the destination's health become more likely. Beginners often ignore scope and focus on the most visible complaint, but scope is a multiplier of reasoning speed because it tells you whether the cause is local or shared. A link issue is usually local to an interface and its immediate port, while higher layer issues can span broader areas. Using scope early prevents you from spending time at the wrong layer and helps you communicate accurately to others about what you suspect. Finally, it's worth reinforcing that link problems are not only about getting back online. but about ensuring the connection is truly healthy after recovery. A temporary fix that restores link-up status but leaves negotiation unstable can create recurring incidents that feel intermittent and hard to explain. A stable link should remain up consistently, negotiate expected characteristics, and carry traffic without excessive errors, because error-heavy links create hidden latency and downstream timeouts that mimic application problems. For Linux Plus thinking, the emphasis is on reasoning. You identify where in the connectivity chain the failure occurs. You decide whether the failure is physical attachment, negotiation alignment, or higher layer reachability, and you choose the next check that reduces uncertainty most. When you can articulate that logic, you demonstrate real operational maturity. You also build confidence, because link issues stop being scary mysteries and become structured problems with recognizable fingerprints. That is exactly what you want as you move into more complex networking topics.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.